when we do static, so we do circuits, it's got to be the RC circuit. Right? You've got to know how to go through the entire process of doing the charge on an RC circuit, doing the voltage on the resistor, doing the voltage on the capacitor, doing the current in the system, but you also know what to expect. Like from the T equals 0 and the T equals infinity, you know what to expect. So there's like kind of vocabulary we'll go over really quickly, but then we do want to hit that RC circuit real quick. So things to remember like Ohm's law, and when it says that something is ohmic, it just means that it follows Ohm's law, right? I don't know why you get to call that a law if it doesn't work for all things, but things that are ohmic follow Ohm's law, okay? That just means for a wide range of voltages, the resistance stays the same. So like a manufactured resistor that you use in electronics, it has the same resistance for most practical electronics. Light bulbs, especially like the older incandescent style, because they're heating up and they get really, really hot, their resistance would change over time because of the heat and because of the thermal energy. So if you were to graph the voltage versus the current, you don't get a straight line for a non-ohmic object. For an ohmic object, you get a straight line when you do V versus I, and the slope of that line is the resistance. Does that make sense? So just ohmic versus non-ohmic, okay? Equivalent resistance, equivalent capacitance. It's similar mathematically, but when you put two resistors in series, you add them because it makes a larger resistor, right? If I want to shove current down the same pathway and there's multiple resistors in series, then they just keep using up energy, and that means there's more resistance. But for capacitors, when you have them in series, you actually get a worse capacitor. You get a worse capacitor. Because remember that if you have capacitors in series, there's like physical gaps between the plates. So what happens is only the first plate and the last plate are actually getting new charges from the battery. Everything else in between, because of the physical gaps, are basically, they're neutral. What's happening is positive and negative charges are just separating, but that overall inner gap there is basically neutral. So you could pretty much call it equivalent to a capacitor where the plates are much further away. And you know that separating the plates with a greater distance makes a weaker capacitor, right? Because capacitance relies on how much you can make the charges attract. So that's why when we have capacitors in series, the capacitance goes down. So we use the inverse sum rule, right? So the 1 over C1 plus 1 over C2 is equal to 1 over C equivalent. But that's the exact rule that we use for resistors in parallel, right? Resistors in parallel, you use the inverse sum rule. Capacitors in parallel, interestingly enough, you just add them up, right? And that's because each plate of parallel capacitors has a direct connection to the battery. So it's got that connection to the source of charges that can then fill each of the capacitor plates. So hopefully that makes sense. The capacitors in parallel actually add up like resistors in series. Good? All that is okay? All right. A non-ideal battery, I just wanted to make a mention of this because you might see something like this where they say ideal battery versus non-ideal battery. So over time, number one, batteries, they will eventually run out of the chemical reaction that's creating the voltage, right? But also, batteries have internal resistance that actually uses up some of the energy. So, and I want you to actually try this with your car. If you have the lights on in your car, okay, so imagine you have your lights on in your car, and the lights are connected to the battery, right? So, if you turn the lights on, they will run at full 12 volts or whatever the battery is, and everything is great. And everything else, like, let's say, the starter of your vehicle, is connected in parallel. So it's also going to get the full 12 volts. What I find really, really interesting, you can see this happening in real time. If you turn the lights on, and I'll just put a switch here. This is your key going into the keyhole, and you close that switch, and you start engaging the starter, okay? Have you ever seen somebody with their lights on who starts their vehicle? You probably haven't even noticed it, but you probably, like, you saw it, but you didn't think about what was happening. The lights will flash as the vehicle is starting. So what happens is the lights are losing a little bit of energy. They're not getting all 12 volts. Well, what the heck is happening? If I take a voltmeter and I put it on a 12-volt battery, I get 12 volts. Does that make sense? If I take a voltmeter and I put it on a 12-volt battery, I get 12 volts. However, that battery has its own little internal resistance, and the older the battery gets, the greater that resistance gets as well. So think about the difference. If I just take a voltmeter and I plug it into the battery, then I get 12 volts. But somehow, when that circuit is completed and I keep my voltmeter on the battery, the voltage reading is less than 12 volts. Why would that be happening? What do resistors do when current goes through them? They take some voltage, right? So if this is a 12-volt battery, and if there's no current flowing through it, it says 12 volts. But as soon as I hook it up to a circuit, and there's actually current flowing, the current that goes across the internal resistance gets used up, and there's a little bit of voltage right there being used up by the internal resistance. So now my voltmeter doesn't say 12. So why is it that your lights would stay on, they'd be working great when you don't engage the starter, but when you do engage the starter, they flash, and they actually get a little bit dim until the car starts. And the reason is the starter and the lights are in parallel. And what happens when you add things in parallel? Like if I plug too many things in my house, okay, it splits off. And what does it do to the overall current coming out of the source? Right? What happens when you add things in parallel? When you add resistors in parallel, the overall resistance goes down. Not worse, it goes down. Which means now if I'm driving the current with a 12-volt battery, but the overall resistance of the circuit goes down, more current is coming out of the battery. So what happens with the internal resistor of the battery? If more current comes out, there's more voltage used up by the internal resistance. So it's kind of like a weird battle there where you end up with a circuit that's asking for more current. So more current comes out of the battery, so the internal resistor ends up having a higher voltage. So the voltage on the lights drops. Right? If you do a closed loop here, you have a giver, that's the battery. You have a user, who is the bulb, and you have another user, who is the internal resistance. So they can say an ideal battery, and that just means that you don't have to worry about the internal resistance. It doesn't exist. If it's a 12-volt battery, it's going to have 12 volts even if there's current flow. If it's a non-ideal battery, the only thing that you would need to do is after you draw your battery, you add a little tiny resistor, and then you can go on and you can create the circuit anywhere you want. So I like to put a dotted line around it showing that that's my battery, and that battery has a little tiny internal resistance. So maybe they put together a circuit like this, where it's just a battery with a resistor, and they ask you to find what's the current in this circuit if it's a non-ideal battery. If it's like, a real battery that has internal resistance. So what I would do with this, I would say, that's my voltage source. It has a voltage of epsilon. If it was a 12-volt battery, I'm going to call that 12. And then I would just do one loop, right? The loop rule here says, instead of just being V minus IR equals 0, what additional voltage do I need to consider? It's just this guy right here, IR. Okay? So it just kind of limits the voltage that the components actually get. So I really don't know which way they're going to approach a circuit problem. They could give you an ideal battery, or they could give you a non-ideal battery. It's just an extra resistor. That's it. So what can I do with these two resistors that happen to be in series? I could just factor out the I, and boom, there you see R plus R, right? They're in series, so I can just add those resistances together.
So you factor out the negative.
So I might do something like this: V minus I times R plus R But guess what that is right there? That's the equivalent resistance of two resistors, okay, in series. We feel okay with that? All right. Cool. Power, right? Power PIV is kind of the way I have that memorized. PIV, P with IV. But if you use Ohm's law and replace V with IR, you also get I squared R. So power, energy, those sorts of things. We need energy capacitor, 1/2 CV squared, 1/2 Q squared over C. There's one other way you could write that. Again, just replacing, like if I wanted to replace, let's say, C with Q over V, then I could find the third way to write the energy of a capacitor. Energy of an inductor, 1/2 Li squared. So inductors have energy when the current is high. When the current is high, their magnetic field is greatest. Capacitors have max energy when the voltage is high, right? When the voltage is high, it has the greatest electric field. So capacitor stores energy in the electric field. Inductor stores energy in the magnetic field. And that magnetic field is going to be greatest when the current is highest. Good? So 1/2 CV squared, 1/2 Li squared. I think the reason that I prefer 1/2 CV squared is just because they both end up looking like a kinetic energy type deal, like a 1/2 something squared. All right. I wrote this here, and I actually have the answer up. But I've seen this in the past where they say, draw a circuit. Like actually draw a circuit where a capacitor could be charged by a battery, and then you can flip a switch to discharge that capacitor through a resistor. Right? So we've seen this kind of deal where I've got a switch that can go either way. The battery can drive the charge onto the capacitor, and then you can switch it over, and the capacitor can then discharge through another resistor. Right? So, is that, yeah?
So the second resistor current is the battery now.
So, their place, I mean, it matters in charging up the capacitor. Because remember that your time constant is RC. So I made them the same in this picture because RC affects how quickly it charges up and how quickly it discharges. But that's all that it would affect. And the location of the resistor, whether it be here or down at the bottom, that doesn't matter because there's not really a sequence to it. It all happens simultaneously. We use the flow analogy, but it's not really flowing. It all happens at the same time. No, but let's imagine if we say RC, the product R times C has something to do with how long it takes to charge up, and you don't put any resistance in. Like imagine you have a battery and a capacitor. Technically, from what we've learned, that capacitor would charge fully instantly. Like what this is suggesting is that it wouldn't take any time. Now, if you do that in real life, you put a capacitor directly to a battery, it doesn't charge instantly. There's a little bit of a delay. What do you think that delay is from? Yeah, the actual resistance of the wires, the battery. But they wouldn't do that to you because, we would, from what we've learned, that would tell us that the capacitor charges up instantly, which it doesn't in real life. So we put that resistor there to just slow the charging process, and then the resistor over here to slow the discharging process so it doesn't happen instantaneously. All right. What would this circuit do? Just a quick sample problem. At t equals 0, what's the capacitor acting like? Right? Capacitor is acting like a wire at t equals 0. So if it's acting like a wire at t equals 0, what would happen to, let's say, the voltage on the resistor? Voltage on the resistor is 0. Why? What kind of circuits? So when I say t equals 0, the moment that I close the switch? Yeah. This is actually pretty dangerous, right? So immediately after closing the switch, it would become a short circuit. Because you'd have a path that would be free, right? It's a free path to go into the capacitor, and then they would charge up. And then sometime later after it charged up, we'll say t equals infinity, then what would happen? Okay, it cuts off that branch. So what would the voltage on the resistor become? Whatever the battery is.
What would the voltage on the capacitor be? Well, why did the capacitor shut off that branch? Because it's full of charge. So the capacitor would also have a voltage of epsilon. Because it's in parallel with the resistor. The resistor was not equal to epsilon initially because the current was 0. But V equals IR. So once the current got going, then it was same voltage, right? But if T equals 0, when this was a short circuit and all the charges wanted to go onto the capacitor, nothing was going to the resistor, okay? And then we could also say, like here, the charge at T equals 0 was 0. The charge now is just C times epsilon, right? CV we're charged up. Capacitance times voltage. Any questions there? All right. Differential equations, this is kind of the meat of the circuit stuff. And I would expect a free response where you have to do something. Okay? So the differential equations, you're always going to start with a loop rule. Right? You always start with Kirchhoff's loop rule. You draw the circuit, you go around one loop. Whether it's an RC charging or an RC discharge, whether it's a LC circuit, you're going to do a loop rule.
Good afternoon, this is Mr. Myers. I just want to remind all seniors that on Monday.
So if you have an inductor in a circuit at T equals 0, does it shut down its branch?
If T equals 0, it shuts down its branch. If T equals infinity, it says yes. Yep. All right. So the differential equations that we'll look for, like if they say write a first order differential equation, you get it to a derivative equals something, and then you're done. You don't have to go any further. But if they say solve it, like that's when we're looking for, you know, current as a function of time, voltage as a function of time, those things. Okay? But kind of the hidden derivatives that we'll see, definitely, you know, I is dq dt. Right? It's kind of like a charge velocity. If you think about current, it's kind of like a charge velocity. So we have that derivative dq dt. But then when you're discharging the capacitor, we said minus dq dt. Because the direction of current was actually opposite the accumulation of charge. Charge is coming off the capacitor, so we said minus dq dt. And that set us up for that discharging exponential decay functions. Okay? The other differential that you're going to see would definitely be with, you know, the voltage on an inductor. That's the minus L di dt, the voltage on the inductor. I don't usually put the minus because I take care of the minus when I mark the high and low energy side on the circuit diagram. But again, on your equation sheet, it's going to say minus L di dt. Okay? The good thing is, if you think about it, you know what the graphs are. So your only job is to figure out the time constant. That's it. The calculus is just figuring out the time constant. You know what the graphs look like for all of them. For RC, LC, you know them. For an RC that's charging up. So you have just a resistor and a capacitor in one loop. What should the current be? It should be a decay. Current is decaying, and even more specifically, it's decaying from epsilon over R. Right? It's decaying from max current. What would the voltage on the resistor be? Also a decay, and it's decaying from epsilon. It's decaying from the voltage of the battery. The voltage of the capacitor, that's approaching epsilon, and how about the charge? And it should be approaching C epsilon, right? CV, we're charged up. So you know what those are. You know what the result is. You just have to produce Y. Y is that the result? And you have to produce the time constant. Okay? For the discharge, they're all decayed, right? Every one of them is decay because you don't have a source of charge anymore. When you remove the battery and you discharge the capacitor through the resistor, you're going to lose charge, the current's going to drop, the voltages are going to drop, you're going to end up with zeros all across the board. Okay? For the LC circuit, or sorry, the LR circuit, the inductor is going to act like an infinite resistor at the beginning, right? But eventually it's going to become a Y. So what would the T equals 0 case, what happens when T equals 0? Right? The inductor gets all the voltage, and it's able to fight. It's able to fight the battery. So at first there's no current, and all these voltages on the inductor, And then eventually, the coil of wire is going to become wire, right? It's going to lose the battle. And at the end, the current becomes epsilon over R. The voltage on the inductor becomes 0, and the voltage on the resistor becomes epsilon. Right? So eventually, the inductor loses. Yes?
Can you just assume like epsilon? I got
It's the voltage of the battery.
is that just always?
That's what they'll use typically for an ideal battery. Like, those, you know what I mean? Like, when they're not in the midst of saying this is a real life battery that has internal resistance, they'll typically use that instead of B.
Okay.
It's just the
So
voltage.
epsilon.
Yes.
What did
Yeah.
epsilon?
Voltage. Yeah, the minus L di dt, that is just voltage. Technically, it's electromotive force. That's voltage. It's just voltage. All right. How about the LC? I thought the LC was the most interesting because LC, you know, is like this really cool passing back and forth of energy. The LC circuit, what's the result going to be? The result is going to be simple harmonic motion. We've got to know that. We've got to be able to hit that quick if it's a multiple choice. If it's an LC circuit, it's going to be simple harmonic motion. Okay? The LC with a battery is interesting because the voltage on the inductor, is going to be a cosine function. Okay? So the voltage on the inductor is going to be a cosine function for sure. Because remember, at t equals 0, all the voltage goes on the inductor is able to fight the battery, and it has to equal epsilon, right? The total voltage, though, just from a loop rule, the voltage of the capacitor and the voltage of the inductor, it has to equal the voltage of the battery, right? You have a giver and you've got two takers, so they have to add up to the voltage of the battery. So if the inductor is a cosine, then it's actually going to make the capacitor voltage 1 minus a cosine, right? Just imagine if I take 1 minus cosine plus cosine, then I get 1. And if I put an epsilon in there, epsilon times 1 minus cosine plus cosine is going to give me epsilon. So the voltage of the capacitor and the inductor have to add up to epsilon. So you get 1 minus a cosine. So that's weird. It's like a negative cosine, but it's shifted up by the amplitude. So it ends up being something like this. Right? So the voltage of the capacitor is 1 minus cosine. So that when I add those two graphs together, it just goes across straight, it's epsilon. Good there. But when you remove, do I not have this on here? So when you remove the battery, so if it's just a charged capacitor and an inductor. So capacitor, inductor. Again, what are you going to see here? Simple harmonic. If it's an LC, even if there's no battery, you get simple harmonic motion, right?
That thing would sort of.
If these are the only two things in the circuit, what do you know about their voltages? They have to be equal. So it's interesting here that one is going to be a cosine and one is just going to be a negative cosine. That's it. They just one's a positive cosine, one's a negative cosine, because when you add them together, you have to get 0. You have to get 0. And that's just a loop rule, right? They're the only two things in there, and they have to be equal. But it is, again, simple harmonic motion, right? The capacitor starts to try to discharge. At first, the inductor is like, no way, I'm going to fight this, but it starts to lose, so current starts to flow, right? But when the capacitor runs out of charge and the current starts to decrease, now the inductor has a change of heart. And it's like, wait a second, I don't like that I'm now losing the magnetic field that you created. So then it starts putting a voltage in the opposite direction, which starts accumulating charges on the capacitor in the opposite direction. So that's why we're getting, again, simple harmonic motion. This is very much 100% going to be a conservation of energy question on the exam. 1/2 CV squared, 1/2 Li squared. All of the energy there at max, all the energy here is when the exact voltage is met.
When you add them equal to zero.
And anywhere in between, not so much equal to zero, but equal to either, so when all the energy is in the capacitor, you do 1/2 CV squared.
Yeah.
When all the energy is in the inductor, 1/2 LI squared. Any time in between, like when you've got a middling current, it's not max, it's not zero, then you're adding up 1/2 CV squared plus 1/2 LI squared, right? But we know, if they give us current, then we can find the total mechanical, and I don't want to call it mechanical, total electrical energy. If they give us the voltage of the capacitor, then we know the total electrical energy. And we can use that to predict the other one, right? So if they give us max voltage, we can predict I max. If they give us max current, we can predict V max. Yes, they will be equal because it's just a passing of energy from one hand to the next. Kind of like when you saw, GPE turning into kinetic energy. You could always use height to predict the speed at the bottom, or if somebody gave you the speed, you could always work backwards to predict the height, and that's exactly what's happening here as well. Any questions at all? Yes?
Well, not almost, but on Monday, since they're doing a picture like okay, are we doing anything?
What is the picture?
I was gonna do a math.
Okay, because
It's all right, I'll do the
When is the picture?